Hello, my name is Omalde and this is Lab 2, Motion of a Following Object. Introduction. The purpose of this lab is to explore Newton's second law with a non-constant force and therefore a non-constant velocity. It is also to explore the impact of drag on a falling object's velocity and finally to briefly discuss terminal velocity. In this lab, we'll be looking at the following models and physics principles. Firstly, we will be looking at two forces, gravity, which is constant, and then drag, which is a non-constant force depending on the velocity of the object. Then we will also be using the models of the position and velocity update formulas as well as the force of drag formula. Finally, since we'll be using the principle of non-constant velocity as the object changes velocity while falling. Final result of this lab shows that a prediction model with drag is best able to predict the observed results. My experiment consisted of dropping a tape from high above ground onto the floor. In this case, the tape was the system while the air surrounding it was the surrounding. For this experiment, I had the following initial conditions. My height was 600 centimeters or 6 meters. My time started at 0 seconds. My initial velocity was at rest. I had a gravity of 9.8 meters per second squared. My drag was 0 since there was no velocity, and the tape was about 1 gram. On the right, you can see me using the tracker application to track the motion of the falling tape. While building a computational model based on this falling object motion, I constructed two models. The first model only took into account gravity, which you can see here in the F-net vector, while the second model accounted for gravity and the drag force, which can be seen in the red squares. My final drag coefficient was about 0.55 after adjusting the prediction model to match the observed data. Here you can see the results of my predicted data. Although both graphs have a declining slope, the slope for model 2 declines much more faster. Here you can see all three data sets overlaid into one graph. One similarity between all the graphs is that they all see a decline in velocity, which means that magnitude increases in the negative direction. The most similar models are the observed models and model 2. Some differences are that some of the slopes are significantly steeper, particularly the ones with drag or the observed models. The most differences can be seen between the two prediction models. Discussion. Some possible errors I had while working on this lab board. The tape may have experienced uneven drag force due to its shape not being spherical. The tracker unit may also have some error as it cannot exactly know how long a meter is in the video. Finally, while manually tracking the object frame by frame, I may have some manual errors. So what do these results mean? Firstly, the observed motion followed the prediction model that had drag in it. These suggest that following motion indicates that is non-constant and indicates the existence of drag forces. Newton's laws of motion were observed because since the net force on the object wasn't zero, there was some level of acceleration as the object fell down faster and faster. Finally, we observed the non-constant drag force, which increased in magnitude as the velocity increased. So of these models, which model predicted terminal velocity? To briefly describe terminal velocity, this happens when an object is falling, but the net force on it is zero because the force of drag equals the force of gravity. Hence, the object starts moving at a maximum constant velocity. However, none of the models in my experiment had a constant velocity at any point in time. Therefore, none of my models approach terminal velocity. Now, however, what if the object was thrown down with negative initial velocity? Well, even though the object starts with a different velocity, since the terminal velocity only depends on the force of drag and not on the initial velocity, the object will still reach the same terminal velocity as in the previous case. Thank you for watching my lab report.